What we're going to do next is learn how to break down any matrix that has complex eigenvalues. And we can break it down into this form, PCP inverse. And I know that that looks like diagonalization, and it's similar, but the middle matrix here, it's C, it's not going to be a diagonal matrix. But it is going to be in this form, A minus B, B, A. So what we can do is we can take any matrix that does have complex eigenvalues, and we can break it down into a form that is a little easier to work with as far as transformations go. So the first thing that we need to do, we need to figure out what A and B are. A and B are going to come from the eigenvalues. So the first thing that you should do is pause this and look for the eigenvalues of this matrix A down here. What we should get is we're going to get eigenvalues of 2 plus or minus I. And if you got that, you can skip ahead in the video a little bit. If you didn't, I'll just show you what I have. So I have 1 minus lambda, negative 2, 1, 3 minus lambda, equals 0. And what that's going to give us, and I'm going to cheat a little bit and just go right to my equation. And using the quadratic formula, I ended up with 4 plus or minus root negative 4. I'm just going to write that as 2i all over 2. So 2 plus or minus I. And what we need to do is we need to also find the eigenvector, or the eigenvectors that go along with this, but really we just need to find one. So if you look up here, this general form has A minus BI. So what I'm going to do is I'm going to take lambda is 2 minus I, and I'm going to find its corresponding eigenvector. And if you pause this video, try to find the eigenvector, that would be good. Otherwise, I'm going to have my matrix. If I take 1 minus 2 minus I, I'm going to have negative 1 plus I. Negative 2, 0, 1, and 3 minus 2 minus I is going to give me 1 plus I. And if I look at this bottom line, if I look at the equation, x1 plus 1 plus I, x2. x1 is going to be negative 1 minus I, x2. So our vector would be, so if x1 is negative 1 minus I, x2, and I let x2 be free, I'm going to have a vector, negative 1 minus I, 1. And I'm going to write this in kind of a funny way, which will maybe make sense in a minute. So when we look at this general form, so C is A minus B, B, A, and we found that lambda is A minus BI, 2 minus I. So that's going to give us our matrix C is A, which is 2, minus B is negative 1. When we look at the eigenvalue A minus BI, whatever number is here, whatever the coefficient is going to fill in this spot here. So the coefficient for I was negative 1, so I'm just going to have a negative 1 here. Don't worry about changing the signs. That's the reason why we took our lambda to be 2 minus I instead of 2 plus I. It just makes the signs identical. 1, 2. So that's how we find matrix C. And then matrix P, let me change colors. Ooh, didn't realize I was highlighting. Okay. So matrix P is going to be composed of the eigenvectors. So P, here it says real and imaginary. What that means is P is going to be 2 by 2, And the real part, so the real part of the formula is the real numbers that compose this eigenvector. So the real parts are -1 and 1. And then imaginary vector, so those are the two coefficients for I. So these coefficients here are going to be the real column. These coefficients are going to be the imaginary column. But we only need to put in the coefficients. So I'm just going to put -1 and 0. So we find P by looking at the eigenvector. The first column of P are the real parts of the vector, and the second column of P are going to be the imaginary parts. And by that, I just mean the coefficients. So that's how we do one problem. So try to do the practice problem next using this as a guide. And I'll go over it in next slide. So if I look at the next problem, so again, pause this if you haven't had a chance to try it. My answers, just so you can check, and if you don't have to watch this part of the video, you don't have to. I got C as 2, -√2, √2, 2. And I got P as 1, -√2, 1, 0. So I'll go through how to get that, but if you got it yourself, then you can close out of this video. That's all I got for you. So if you did not get that, so first we need to find the eigenvalues and one corresponding eigenvector. So to find the eigenvalues, I'm going to have 3 minus lambda, -3, 1, 1 minus lambda equals 0. And again, I just kind of didn't show much of my work, but lambda squared minus 4 lambda plus 6 is my equation that I found for that. That's going to give me lambda is 4 plus or minus √16 minus 24, so that's 8, -8, -8, all over 2. 4 plus or minus, 2i √2 all over 2. 2 plus or minus I √2. So if I use lambda as 2 minus I √2, we can use that to build matrix C, which I will erase and just kind of show you. Why aren't you erasing? There we go. So C has the form A minus B, BA. A and B are the coefficients for the eigenvalues. So here A is 2 and B is √2. So remember here we just keep the same sign as that eigenvalue of A minus BI. Okay, so that's going to be C. I need to find the eigenvector to find matrix P. So we have what? So 3 minus 2 minus I √2 is going to be 1 plus I √2. -3, 1, and then 1 minus 2 minus I √2 is -1 plus I √2. 0, 0. If I use the second line, I'm going to have x1 plus -1 plus I √2, x2. So I have x1 is 1 minus I √2 times x2, which is going to give me a vector of 1 minus I √2, 1. And if I look at that as 1 and then 0, because to find p, we take the real parts. So these first numbers, those are going to give me the first column of p. So I have 1, 1. And then the second column of p comes from the coefficients of the imaginary numbers. So negative I root 2, I'm just going to have negative root 2. And then 0i, I'm just going to have 0. Okay, so that is how we would find this breakdown, PCP inverse. If this video and the other video made sense to you, I think you're ready for the to try out the worksheet that's going to be graded. If you want more practice stuff, just reach out to me and let me know, and I can help you with that sort of thing. Okay, so yeah, let me know, and I hope you found this helpful.